atomic scale modeling and simulation can drive innovation in this rapid evolving field. Following this, Dr. Hariharan will present his research on the density function theory based insights into the VOC sensing using the Synopsys QuantumATK software. His talk will highlight how advanced computational simulation are enabling breakthrough in the next generation sensing application. So with this brief introduction, I am delighted to hand over the session to our first esteemed speaker, Professor Kala. Over to you, ma'am.
Okay, sir. Thank you, sir. The screen, can I share the screen or? Hello, sir. The presentation, can I share the presentation?
Yes, ma'am. Yes, ma'am. Please share your presentation.
Okay. Okay. It's visible, sir?
Yes, ma'am. It is visible.
Okay, sir. So, very good afternoon. So, thank you for the nice introduction. So, first of all, I'd like to thank the organizers of this webinar series, featuring Synopsys QuantumATK, for providing this wonderful opportunity. So, today I'm going to talk about density functional theory based atomistic simulation for next generation gas sensing applications through functionalized MoSe₂ monolayer. Before enter into the core research, I would like to give an overview about atomistic toolkit. So atomistic toolkit is one of the standard simulation tool for atomic scale modeling and simulation. This will provide a pathway for discovering, optimizing, and utilizing novel materials by integrating multiple simulation engines like density functional theory, semi-empirical approach, force field, the combination of density functional theory and non-equilibrium Green's function, and so on. This QuantumATK will consist of system configuration and a very user-friendly virtual nano lab, and we have different calculations also. In system configuration, this will provide a very broad spectrum of materials from molecule to device. So it's possible to configure a single molecule, polymers, 1D, 2D materials, crystals, amorphous materials, 2-terminal as well as 3-terminal devices also. These configurations can be achieved by, or it can be done by process of building tools and a standard database for whatever the structure we are going to configure. And additional feature is the output also visually we can analyze with the help of this virtual nano lab. Depend upon the size of the system what we have configured, and different simulation engines can be chosen. Suppose the system is a very smaller one and it is consists of less than 100 atom, then density functional theory plane wave calculation itself is highly support for all the calculations. Whereas if the system is a little bit larger, which consists of more than 100 atom, then density functional theory with linear combination of atomic orbital will be a proper calculation for all this analysis. In addition, suppose if your system is very larger, either we can go with the semi-empirical approach or we can go with a force field. So like different calculations depend upon the size of this system. So whichever the calculation will be suitable, and that can be adopted. The QuantumATK, this will address different material modeling areas, which will include semiconducting materials and its applications, energy-related applications like batteries, solar cell, fuel cells, and so on, and also gas sensing applications, catalytic applications, then the polymer drug delivery relevant applications. So all the things can be addressed by this QuantumATK. When we come to this QuantumATK, just a minute. Yes. So the processing of QuantumATK will consist of 3 different steps. So at first we have to generate an input file with respect to our system. we have to provide a necessary basis set, and we have to choose the pseudo potential, and all other parameters need to be given, and the proper input file need to be generated out. Then depend upon the system, so we can choose what suitable calculator. So it can be a density functional theory based calculator, or it's a force field, or it's a semi empirical calculator, whatever. So once the ground state properties are analyzed, then towards our applications, additional analysis can be done, and it can be based on the material property. Suppose if it is a device, then device property analysis that can also be done. So these are the different simulation process which will take place in quantum ATK. So in our institution, we have a computational material science and nano device simulation laboratory, and we are working on 4 different research areas: 2D materials for gas sensing and biosensing applications, organic molecule for molecular junction devices, especially for electronic applications, and functionalized carbon nanostructures for drug delivery applications, and heterostructures for thermoelectric applications. Along with me, Professor John Tiruvadigal and Dr. R.M. Hariharan and Dr. Janani Shivashankar, and these are the faculty members whoever is working in these research domain, and some of the research outputs relevant to this research domains are highlighted over here. In the simulation laboratory, we have quantum atomistic toolkit with 4 virtual nano lab. In addition to quantum ATK, we also have other simulation tools also, but predominantly we are using this quantum ATK only. So using this quantum ATK, as of now, we have produced 12 PhDs, and currently 25 research students are working, and 10 to 15 undergraduate and postgraduate research problems are undergoing. And for the last 10 years, we have produced around 82 publications through this quantum ATK. Well, come to this research problem. Air pollution is one of the major issue that will generate a very strong impact to the environment and human life. The main cause of this air pollution comes through the industrial pollutant, agriculture waste, automobile emission, and various pollutants which comes from the residential sector also. This will create a very large impact, like numerous health issues and environmental consequences. So sensing such a toxic gases is a vital one for human safety as well as environmental protection. So one of the solution for this issue will be the gas sensor. So when we come to the gas sensor, the sensing material will play a vital role here. Or the sensing material, it can be a metal oxide, conductive polymer, or it can be a nanomaterial, whatever. So when the sensing material is exposed to any toxic gases, this will make an interaction with the toxic gases, and depend upon the concentration of the deduction of gases, an internal resistance will be created out, which will generate a voltage. Based on that, the analysis will be done. Well, come to the gas sensor. The efficiency of the gas sensor will play another important role over here. So the efficiency of a gas sensor can be achieved by considering a variable parameters like sensitivity, selectivity, recovery time, stability of the sensing material. It must be cost effective, and power consumption also we need to consider, and it must have a very low response time, and so on. All these features will make the sensor to perform accurately, reliably, and it will produce an effective deduction of gases towards any kind of toxic gas. So this efficient gas sensor can be achieved by selecting a proper sensing material. So our research is focused on gas sensing material only. Well, come to the material, as I mentioned early, a different material can be used, in which nanomaterial is an excellent candidate to sense the toxic gases due to their unique properties like high surface to volume ratio, and it will have a tunable properties and fast response and recovery time, and so on. We have a different class of nanomaterials: one-dimensional, two-dimensional, three-dimensional, and zero-dimensional, in which we have concentrated on 2D material. This is one of the predominant material towards gas sensing. So in 2D material, if you form a layered form of a monolayer or a heterolayer, whatever, a layered structure of 2D material if you form, then it is very easy to make every atom to expose to the toxic gases. for interaction, which will highly needed for the detection of toxic gases, and it's also have a highly tunable electronic structure. So again, come to this 2D material, we have a different class of layer 2D material in which our researchers mainly focus on 2D chalcogenides. So out of this chalcogenides, one of the chalcogenides, that is molybdenum diselenide, how it will be interact with the toxic gases and how it can act as a very good sensor, and that analysis alone just I'm going to, that is some of the results related to MoSe₂ gas sensing. Right now I'm going to validate. Come to this MoSe₂ material. So this is the layered structure. It will have, in general, it will have a very good chemical stability, and it will have very high adsorption activity. And it's also one of the predominant platform for gas sensing analysis also. While come to this MoSe₂ monolayer, so what we have done is, first we have formed the unit cell. Then we have repeated the unit cell with respect to the X and Y axis. That is in 4 times, that is 4 cross 4 cross 1 supercell we have formed, and that supercell will act as a monolayer, and that we consider as a base material for all the analysis. When we come to this MoSe₂ monolayer, so the monolayer will consist of molybdenum atom, which is sandwiched between 2 layers of this will have the structure of this MoSe₂ monolayer will make it more attractive towards sensing, and the electronic properties of this material is also highly tunable by means of functionalization. That is also what possible. Whenever if you choose any material for gas sensing, certain parameter we need to consider. So one will be the compatibility of the material, and the material must be cost effective, and easy source of availability we have to look into. It must have good electronic properties towards sensing. In addition to all those things, the validation of the material with the experimental findings, and that also we need to consider. So based on all those things only, the selectivity of the material will be done. So I'll come to the work structure. So at first we need to take a base material, which is a pure form of MoSe₂ monolayer, and that has to be optimized. We have formed 4 cross 4 cross 1 supercell, and that we used as a pure MoSe₂ monolayer. Optimization we have done. So after that, the basic ground state property analysis we have done, and the properties like band gap and the bond length and the bond angle, such kind of basic parameters are validated with the reported theoretical and experimental results. Then to enhance the property towards adsorption, the functionalization of the material has been done. So in general, the functionalization can be done by introducing the defect like vacancy creation, or by doping process. Doping process, it can be a substitution doping, or it can be a add-on doping or industrial doping. Applying stress and strain is also one of the way of functionalizing the material. But here we have chosen only the add item. In this work we have, but vacancy, creation of vacancy, as well as stress and strain applications, and that work also we have done. But here we have incorporated only the add item. By incorporating the add item, by the way, we have enhanced the property of the material towards gas sensing. So after the functionalization and the gas sensing analysis need to be done by adsorption study. So this is the general work structure when we go for any material for gas sensing application. For all these theoretical analysis, and these are the computational data, what we have, computational parameters, what we have used, and we have adopted density functional theory for all these calculations. And this is the optimized structure as well as doped systems. Pure MoSe₂ monolayer, we have achieved the band gap is 1.4, comes closer to 1.5 electron volt. So it is well matched with our results. So in such a way, we are validating our base structure. Then functionalization need to be done. So for that, we have chosen high transition metals like ruthenium, rhodium, and palladium. These are the 3 different dopant we have what chosen. So generally when we are choosing a dopant, again we have to look into the compatibility of the dopant with our system and the reproducibility of the dopant with respect to the experimental validation. And the most important thing is the dopant must enhance the property towards gas adsorption. That is, the dopant must make the surface more reactive towards the gases. So these are the basic parameters we need to consider when we are choosing any dopant for sensing applications. So here what we have done is we have replaced molybdenum with the dopant, as well as we have replaced calculated out or systematically we have analyzed. But out of those, only the selenium replaced systems is showing a high stability. So that further analysis, we consider only the selenium replaced by a dopant. That system alone we consider for, or the remaining analysis, that is towards the gas sensing analysis. So after incorporating the dopant with the system, so at first we have to confirm the structural modification, whether the structural modification has happened, if the dopant is properly doped with the system, that is interacted with the systems or not. Those things that these are the basic things, and that has to be analyzed. So for that we have measured the bond length as well as the bond angle. So with respect to the pristine MoSe₂ monolayer, the bond length and the bond angles are showing considerable variations. So which implies that structural modification has happened, and that is also reflected in the band gap. A reduction in band gap was observed after creating a very small structural changes, and that we have observed also after incorporating the dopant. So the stability analysis we have done by calculating the formation energy. So it's an exothermic process, and the formation energy values again satisfying the stability, or it is confirming the stability of the system. In addition to the formation energy analysis, we also done the phonon band structure analysis to confirm the dynamic stability of the system. So in all phonon band structure, positive phonon mode corresponding to that of the Berlin zone. So which implies the dynamic stability of the system. And there is a considerable variation in the structure. At the same time, after incorporating the dopant, the system is what stable, and that was confirmed. And the same thing is analyzed by means of the band structure analysis also. So in the band structure analysis, very close to this what system, and that is a charge transfer analysis. So in the band structure analysis, very close to this what system, and that is a charge transfer analysis indicating that right, well reduction in this band gap has happened in the system, and new energy bands are created in the gases when the gases are very close to this what systems. And in addition to all those things, if you see the band gap analysis, very close to this what the energy bands are moving towards the Fermi energy level due to the incorporation of this what dopant. And this changes in this electronic structure which has happened when the dopant is attached with the system, or it is incorporated with this what system, and there is a charge transfer which is happening between changes or happen in the by means of the charge transfer analysis. So here we have observed the positive charge transfer value, and this positive charge transfer value representing that substitute, that is the dopant does act as a donor and the system is acting as an acceptor. The same thing can also be confirmed by the electron density different analysis. So this is the visual representation to confirm the accumulation and depletion of redistribution of charges after incorporating the dopant. So after incorporation of the dopant, how the charges are redistributed among the system, which can be visually understand with the help of this electron density difference analysis. So in electron density difference analysis, the blue color will represents the depletion of the system, and the pink color will represents the electron accumulation. So if you look at the dopant region, so in the case of a dopant region, we can observe only the depletion and not the accumulation. The accumulation has not happened, only the depletion is happening around the dopant. So which indicating, this indicating that around the dopant, we can observe only the accumulation is, depletion is what happened, not the accumulation. So which validating that the dopant will act as a donor and the system will act as an acceptor. Right, so there is a proper charge transfer has happened, which means the dopant is strongly interacting with our system, that is strongly doped with our system, and that can be confirmed. And come to the density impurity peaks very close to this what Fermi energy level, and this is because of the incorporation of this what dopant, and all these modifications are mainly comes because of the d orbital hybridization, and d orbital hybridization is majoritarily observed in this density of states analysis. And the density of from the density of states analysis, again we are validating new energy states, that is impurity energy states are arising close to the Fermi energy level, and this is well matched with the band structure analysis also. So here also close to the Fermi energy level, new energy states are created, and the same thing was observed in the density of states analysis also. Right, so pure system we have taken and three different dopant. After functionalization, structural analysis we have done, and the stability analysis we have done, and the dopant is properly doped with the systems or not, and that can be analyzed by charge transfer analysis too. So now we have to incorporate the gases. So we have chosen a set of gases. So here just I have represented only three set of gas. Generally we are focusing on industrial pollutant. Here we consider only the hydrogen gas and H2S as well as Hessian gases. So for gases, systematically we have analyzed all the possible orientations. Come to the hydrogen gas, only one orientation, that is the hydrogen atom towards our system. Two different orientations are possible. Hydrogen towards the system, that is one orientation, and the sulfur towards the system, this will be the other orientation. When we come to this what Hessian, it's possible to get three different orientation. One will be the hydrogen towards the system, other one will be a carbon towards the system, and this will be the nitrogen towards the system. So these are the possible orientations. In all the possible orientations, systematically we have done the analysis. All possible orientation and different adsorption site studies are possible. One will be the hollow site, bridge site, and top of MO, and top of SC, and top of dopant site. These are the possible adsorption site. Different orientation in all the possible adsorption site, we have done the analysis. So based on that, whichever the orientation and whichever the adsorption sites are showing a better stability and very good adsorption energy, only those adsorption sites and the orientations are considered for sensing analysis. So based on that, this is the optimized structure of hydrogen gas adsorption, that is for pure MoSe₂ as well as a doped MoSe₂ system. And different orientations and the sites also here I have what represented. And this is for the optimized structure for H2S gases, and this is the optimized structure for Hessian gas. In all these optimized structures, we can clearly see how the gas molecules are aligned with the surface. At the same time, the orientations are different, depend upon the dopant. For each and every dopant, a different orientation will be the stable and right towards the stable as well as highly absorbing towards the toxic gases. Only those orientation we consider for all these analysis. And after incorporating the gas, whether the gases are adsorbed by the system is sensing the gas or not, and that can be analyzed by calculating the adsorption energy. And this will be the adsorption energy of all the systems. If you see the hydrogen adsorbed systems, so here the adsorption energy values are very low in negative magnitude. That is, the values are what very lesser. That is minus 0.27 and minus 0.13, right? Okay. So I'm not getting a good adsorption energy value in the case of hydrogen gas, so which implies the pristine MoSe₂ as well as the doped systems. All the systems are showing a very weak adsorption towards the hydrogen gas, since the charge transfer is also very less in the case of hydrogen systems. Whereas if we come to this H2S system, gas adsorbed systems, compared to pristine, all other systems are showing better adsorption towards this H2S gas, all the doped systems. So which implies the doped systems are enhancing the adsorption phenomena for gas sensing. And out of all those things, the ruthenium doped systems is showing a very good adsorption, a least adsorption energy with a negative magnitude, that is minus of 1.13. And this system will be the good adsorbed systems towards H2S gas, and this also showing a good charge transfer value. When we come to this Hessian system, in the case of Hessian, again compared to that of pristine, and all other systems are showing a better adsorption energy value, but comparability, again the ruthenium doped MoSe₂ is showing a better adsorption, and with the least value minus 1.71, and a very good charge transfer compared to all the systems, Hessian systems 0.168 electron. So from this adsorption energy analysis, what we observed here is this doped systems as well as the pristine MoSe₂ systems are not act as a good sensor towards hydrogen. Instead, it can be act as a good sensor towards H2S gas as well as Hessian gases. And these are all further analyzed by means of electron density different analysis. So in electron different density analysis for hydrogen gas, we can see a very slight accumulation and depletion, and which implies a very weak interaction has happened between the gas as well as the system. But if we go for H2S gases, visually we can see a strong charge accumulation and depletion has happened, which implies a high adsorption and large charge transfer is what happening in the system. If we go for this for Hessian system, donor accepted interaction is clearly seen for Hessian gases with the dopant, and these analyses are very visually validate our adsorption energy as well as the charge transfer. Now, the adsorption is happen with respect to the gas as well as our system, but what type of, whether it is a physisorption process or it will be a chemisorption process, and that can be analyzed by means of this electron localization function analysis. In H2S gas, very clearly we can see no bonds are formed between the gases. Bond formations are not exist between the gas as well as the system, which implies the hydrogen gases are interacting with the system by means of very weak physisorption process. Whereas if we come for this H2S, H2X, RH system is showing a chemisorption process, but other systems are showing a physisorption, but it's a very good board physisorption process, a high interactive physisorption with respect to the gas as well as our system, that is doped MoSe₂ system. And if we go for this Hessian gases, the Hessian gases are making an interaction with the systems by means of chemisorption. A proper bond formation is visually we can validate with the help of this electron localization function analysis. Right. So based on all those things, we have taken a pristine form of MoSe₂ monolayer, and that is functionalized with the set of transition metal by means of substitutional doping process. And after the functionalization process, so the gas adsorption analysis we have done by calculating the adsorption energy and by studying the charge transfer relation as well as electron localization function analysis. With respect to all except this hydrogen gas, other two gases are well adsorbed by the doped system when compared to that of pristine MoSe₂ monolayer. And to validate our results, or just to work on at what temperature the sensor will be highly reliable. So we have done the recovery time analysis also. So again in hydrogen, in all the different temperatures, the hydrogens is showing a very small recovery time, and that is not sufficient for a efficient sensor. But in the case of H2S and Hessian, in H2S, very close to this room temperature, that is little bit higher temperature, it is showing a good recovery time, and with that can be act as a good sensor in this particular temperature. Why we have done the recovery time analysis till 673 Kelvin, in the sense MoSe₂ monolayer, and that will be stable more than 700 Kelvin. So based on that high temperature also we have done this analysis. And when we come to this Hessian gas, in the case of Hessian gas, room temperature, right, for palladium, we have observed a good recovery, or considerably good recovery time even at room temperature. But for ruthenium and rhodium, we have observed good recovery time very close to this room temperature, little bit what larger temperature. So from this entire work, the main conclusion part, if you look at, we have done right, okay, yes, structural analysis of pristine MoSe₂ monolayer. We have done the structural analysis for pristine MoSe₂ monolayer, and we have incorporated the dopants, right, in order to functionalize the MoSe₂ monolayer. So the dopants are well incorporated with the systems, and that can be validated with all our results. So after that, right, the gas adsorption analysis we have done. So from this gas adsorption analysis, we concluded that except this hydrogen gas, for all other gases, the system is, except hydrogen gas, all other gases, that is H2S as well as HCN gases, the system is showing a good adsorption towards the sensing. And based on this recovery time, we can conclude that is a palladium doped system can act as a good sensor at room temperature for Hessian gas adsorptions, whereas other doped systems, ruthenium and rhodium doped systems, that can act as a good sensor for H2S as well as Hessian gas also, but not at a room temperature, little bit higher temperature. So these are the main conclusion of that. Okay, thank you.
Thank you, ma'am. Thank you very much for your insightful presentation. Your talk has provided us with a deeper understanding of how DFT-based simulation can be effectively applied to the gas sensing using MoSe₂ monolayers. Now it is my pleasure to invite our second esteemed speaker, Dr. R.M. Hariharan. So he will share his research and the DFT-based insights into VOC sensing using Synopsys QuantumATK, showcasing how computational simulation are enabling breakthrough in the next generation sensing application. So with that, I would like to welcome Dr. Hariharan to take us through his presentation.
Thank you, Deepak. Thank you, Professor Kala Madam, for giving introduction about our laboratory and research activities. Deepak, I am audible?
Yes, sir, you are audible.
Yeah, thank you. So first of all, good afternoon, everyone. I like to thank the organizers, Integrated Systems, for giving opportunity to present my research work in this faculty webinar series. I am pretty much happy to share my work here. So the research topic which I am going to present today is silicene nanoribbons as promising sensors for breath biomarkers, a DFT based study. So this is the topic which I am going to present today. So before jumping into my research work, I like to mention about the research laboratory. As Madam mentioned already, ours is a computational material science and nano device laboratory located in SRM University, Kattankulathur campus. And though we have a particular laboratory here, we have different groups working in this laboratory. My group consists of three research scholars, Mr. Akash, Mr. Shakti Balaji, and Jiva, all three people working under me. And our group research interests are 2D materials for biomedical applications and enhancing thermoelectric property of the 2D materials and ZT values of the thermoelectric devices, and also using organic molecules for simulating and designing electronic devices. So these are the research interest of our group, and for all these works we extensively use the QuantumATK for our research, and we have been doing this for quite a long time. As my work is related to breath biomarkers, I like to introduce the term breath biomarkers. So breath biomarkers are volatile or non-volatile organic compounds present in exhaled breath that will help us to know about the person's state of health actually. So biomarker detection is considered as a non-invasive diagnostic tool for health monitoring. There are three different types of breath biomarkers, sorry. The volatile organic compounds, VOCs, example acetone, hexanol, propanol. The second type is inorganic compounds such as nitric acid, oxide, carbon monoxide, and ammonia. The third one is non-volatile compounds, X, exhaled breath condensate. All these three compounds are present in breath. But our study and our interest lies on volatile organic compounds. Particularly, the early diagnosis of disease is helpful in mortality rate and the cost detection. So that's why we chose our breath biomarker to be a volatile organic compound. So identifying promising VOCs is the first step in framing a health monitoring system, which affects mortality rate and the cost of the treatment. So choosing the right VOC frames the first step. The second step is to identify the suitable sensing platform so that it can have the following requirements: high sensitivity, selectivity, fast response, recovery time, and stability. So the choosing the right VOC and the sensing platform is critical for any health monitoring system. So among the various materials available for detecting VOC, metal oxide semiconductor, transition metal dichalcogenides, metal organic framework, and exenes, we have certain advantages and disadvantages. When we look at all the available platform sensing materials for to be used as a sensing platform, we find exenes having better sensitivity, moderate recovery time, and operational room temperature, and poor selectivity. So that remains the goal of our work. So we have to improve the selectivity of exenes. So we consider this as what to say one of the criteria for identifying a better sensing platform. So a typical characteristics for a sensing platform: the material should have high sensitivity for selected VOC, material with higher or superior selectivity against interfering gases, and it should have a operating state in the room temperature, and it should have a good recovery time. So that led us to the identified biomarkers. Acetone. The acetone is a common biomarker found in diabetic patients, and propanol is again a common breath biomarker present in cancer patients, particularly lung cancer patients. And hexanol is another biomarker which present in COPD patients. Sorry. So we will be using these three biomarkers that need to be sensed by using a nano material. So here, what material we have chosen in the sense, we have chosen silicene. The reason for choosing the silicene in the sense, it has a high surface area, excellent optical property, unique electronic properties, good biodegradability, and desirable biocompatibility. More than that, it has a very good biocompatible nature, making this material very suitable for sensing platform. Particularly, silicene is a zero band gap material, and it has a sp2 hybridization and sp3 hybridization. And when we cut that into nano ribbon, actually, it will show the band gap. So in our present study, we use armchair nano silicene nano ribbon for as a sensing platform. So as I told already, the sensitivity and selectivity remains the main issue that need to be enhanced in X-scenes. There are different ways to increase the selectivity and sensitivity by nanostructuring or through functionalization or introducing the defect engineering or having a doping. So by any of these methods, what we can do in the sense, we can enhance the sensitivity as well as selectivity. All these methods have been adopted already, and it has been confirmed through literature survey as well. So this makes our objective to study the absorption behavior and mechanism of VOCs, particularly acetone, propanol, and hexanol towards the pristine ASNR. To enhance the sensing ability, we will be using the doping, boron and nitrogen, and also we introduce vacancy to see that that will influence the sensitivity. Right, so these are the computational details that we used for our research work. Now coming back to the systems, so what we present here in the sense, we present the pristine nanostructure, defect-induced nanostructure, particularly armchair silicene nanoribbon and boron-based, boron-doped armchair silicene nanoribbon and nitrogen doped armchair silicene nanoribbon. So these structures were optimized, and optimized results are shown in this table. And the stability of each of these structures were confirmed through the formation energy. So all these structures show proper stability, good stability, and that can be confirmed through the formation energy. Now the band gap of the pristine structure, vacancy induced nanostructure, the boron doped nanostructure, and nitrogen doped nanostructure is shown here. So when we introduce the doping, we can see the band gap of the materials when compared to pristine has changed tremendously. We can see that it shows the metallic nature, whereas the pristine structure shows the semiconducting nature, which confirms the influence of a doping. Now coming back to the adsorption sites, since the silicene nano ribbon has a buckled nature, so the possible absorption sites are mentioned here. So we have hill, valley, bridge, and hollow sites. So these are the 4 sites that can be used for absorbing the VOCs. So we kept, we used the first biomarker, acetone biomarker, and for the pristine structure, vacancy-induced nanostructure, nitrogen doped and boron doped and nitrogen doped silicene nanostructure. So it has been kept very close to the when it is optimized, we can see the VOCs are attached to the bridge site of the silicene nanoribbon. In a vacancy, it is very close to the deformed site, and whereas in a doped system, it is very close to silicon atom, and in either case, it has been very close to the silicon atom. The top view and the side view of the same has been shown here. The very same has been done for the propanol. So we used the propanol and we optimized, and unlike in the previous case, here we don't have a bridge, but the absorption site is hill over here. And similarly, the molecules are observed at vacant site and the near the silica in the silicene armchair nanoribbon. And here also it is very close to the doped site, the silica atom near the doped site. And this is for the third biomarker, which is hexanol. And for hexanol 2, the adsorption site is hill for the pristine, and it is absorbed at the vacancy site for a vacancy induced system, and it is once again absorbed in a silica atom near to the dopant site. and for same for boron as well as the nitrogen. So this actually this structure comes optimized structure confirms that doping induces a strong attraction of the VOCs towards the structure. So we can understand it has been effectively enhanced. The adsorption properties have been effectively enhanced. So that can be verified through this table. So the adsorption properties of the silicon nanoribbon can be seen through this tabular column. In the first case, we have the blue color box resembles for acetone, the green color box resembles for propanol, and the light green represents the hexanol biomarker. So if we see very clearly in each of the boxes, it is for acetone, it is nitrogen doped silicon nanoribbon have a strong attraction towards the acetone biomarker. The adsorption energy is the least here. So one can say it is the nitrogen doped system shows a very good absorption properties, which is confirmed through the charge transfer as well as the change in the work function percentage. So the adsorption energy is correlated with here the charge transfer as well as the change in the work function. Similarly, when it comes to propanol biomarker, we can see that the nitrogen doped system has a very good absorption energy again, and which is correlated with the charge transfer as well as the change in the work function. When it comes to hexanol, once again it is the nitrogen doped silicon nanoribbon which has very good adsorption energy as well as the change in the work function and the charge transfer. Now those results were confirmed through the band structure and the density of states. So the band structure of the doped system, the vacancy induced system and the pristine system is what shown over here, and the corresponding density of states is correlated with. This is for the propanol absorbed nanostructure. This is for the hexanol absorbed nanostructure. Now, since from the tabular column 2, we can identify that the nitrogen doped silicon armchair nanoribbon having a very good absorption energy, and it has a strong attraction towards the VOC molecules, and those results have been highlighted. Keeping this into mind, we take the three systems and we converted that into a device. Now a two probe device have been set up for these three devices, and we performed the IV characteristics, and through IV characteristics we calculated the sensitivity, and what we can see in the sense the sensitivity for hexanol is very high when compared to that of propanol and acetone. In the presence of the interfering gases such as nitrogen, H2O and CO2, thereby we confirm that the nitrogen doped ASMR is a very good sensing platform for hexanol biomarker. And remember, hexanol is a breath biomarker for COPD disease. Now, in summary, the structural and electronic properties of pristine, defect-induced, and doped ASNR were studied using DFT calculations, and we found that nitrogen doped silicon armchair nanoribbon has a very good sensitivity, selectivity, and a very good recovery rate towards the hexanol breath biomarker, and this work has been published very recently in the material science in semiconductor processing journal. Thank you.
Thank you, sir. Thank you for this brief presentation. Now the session is open for the question answer. So if anyone has any query, they can directly ask to the speaker.
Thank you for the presentation, Hariharan sir. Can you hear me?
Yes, sir. Thank you.
Could you explain what is the mechanism behind why you chose hexane here?
Sir, actually, any nanomaterial, that's what I told you. Generally, nanomaterial have a very good surface to volume ratio. So particularly when you come to sensing application, when you have a very good surface reactivity, and it will be very useful. And that's why what we use, in the sense we use the Xins, which has a very good surface reactivity.
Only surface is enough because when you compare to graphene, graphene is having a high conductivity as well as high surface area.
Sir,
What do
I
you think?
think
Because
you
silicon
asked,
also having
no, you asked about Xin, right? Now you are
yeah,
talking about
hexane.
graphene. No, you are
No, no,
talking
no, no.
about
I'm
any
asking you.
specific
You
material,
are
or
you are
generally 2D materials.
Exxon. Um, in terms of Exxon, I want to answer. I want to ask you what is the mechanism why it is having a more interaction to silicene.
Yes, so that is what I am telling. See, we have yeah, in the present study we have shown three biomarkers, effectively
Yeah,
acetone and propanol and hexanol. Okay,
yeah,
hello. Ah, so
yeah.
we have three organic compounds, sir, and for all those things, it has not what to say interactive. Obviously, we have to choose a material which is
Yeah, I'm here.
yeah, sensible to a particular molecule. It is not that the silicene is universal and propanol is universal. So we have to see whether the chosen system is capable enough to absorb that particular molecule or not. So it will be case to case basis. And mind you, it is not the silicene, it is nitrogen doped silicene has a better response. Uh, I hope I answered
What
your
kind of
question. If you have anything, you can ask it. Please, sir, tell me.
but I want to know how the interaction is happening. What kind of interaction is happening between the
Sir,
nitrogen? Hmm.
yes. See, the interaction has been validated through the energy level alignment, realignment. That is why the band structure and everything is varying. So when you keep the molecule close to the surface, there will be interaction between the system and the molecule. And because of that interaction, and there will be a realignment of energy levels, and that can be confirmed through the band structure. So it is not that all the molecules will interact with all the surfaces. So that we have to find out. There is no ready-made material that we can what to say straight away use. So silicene may be sensible to hexanol as per our study. It will not be for another biomarker. So that we have to understand. So by studying only we can understand.
Thank you. Thank you for your answer.
Yes.
Sir, please have a look on the chat box as well.
Okay. convert the optimized structure into a device. அதான் கேட்டிருக்காங்க after geometry optimization.
So you can unmute yourself, Unity. I think somebody have raised the hand. If you can ask the question there.
Okay.
Yes.
All right. Thank you very much for the presentation. I have a question for Preferencial C.
Yes.
Okay.
Sure.
Okay. Initially, I asked and she answered me already on the chat. So I want to ask some more, especially when I was using VAS before, not with a quantum ATK. So is it possible to bring my output files and post process using quantum ATK?
Yes, sir. Now you have an interface to do that. Obviously, you can couple it with quantum.
No, they are long process. I don't want to rerun the simulation again. I already have my result from working with VAPs. So I just want to post process. So is it possible, for example, that this electron localization function, that is just what I want to run. So is it possible?
Yes, yes, it is possible.
Okay, okay.
Because the current version of this ATK is incorporating this VASP also, sir. It's interface. VASP and the ATK both are interfaced with each other. So whatever the files we are having in VASP, that as such you can utilize in ATK also.
Okay, okay. Thank you very
Both
much.
are interfaced.
But
Okay.
the version should be the updated one.
Updated. The current version only we will have these features, and that you have to look into.
Even the integration of the Synopsys QuantumATK with the Quantum Espresso, that is also possible. So you can also export their raw data and the QuantumATK.
Yes.
Okay, then on a lesser note, I want to get how you get this charge on each atom. For example, now when we are presenting, like the contribution, for example, like the hydrogen on ruthenium. I just did something like that yesterday. I got my absorption energy. 1 minute, let me check. My absorption energy was 0.78. There was even a reaction. The hydrogen disintegrated and it reacted with the ruthenium. But in your own case, you had a better distance. So I don't know what happened and that there was no reaction in your own. Did you get my question?
Yes.
Yeah.
Can you repeat again? We could not get it properly.
I experimented hydrogen absorption on ruthenium doped on a sheet. My own absorption energy was negative 0.78, while yours is around 0.1 something. So I don't know why there was a large difference like that. And from when I analyzed my Contka, it was there was reaction. The hydrogen reacted with the ruthenium. So why was there reaction in my own? Because to have that kind of high absorption energy, it has gone from physisorption to chemisorption.
I think in your system towards the hydrogen gas, you got a low absorption energy,
High.
right?
No, high.
Yes.
Negative 0.78.
Negative 0.7.
Yes.
But yeah, okay. But okay. Yes, actually the thing is that only we are telling whether it is a pure system or you have done the functionalization, sir.
Yes, I functionalized, but with dope on top of the not replacing, not substitute doping. I just put the ruthenium. No, not substituting doping, just like functionalization on top of the sheet. On top of the sheet.
Okay, add atom. I think you have done the add atom analysis, right?
Yes.
Okay,
Yes.
so what will be the concentration of this add atom with your system, sir? Suppose if you want to improvise, okay, so you can increase the concentration of this add atom, and that will give you more charge transfer, and that will enhance the electronic properties also, and which will be feasible towards gas adsorption. So that may increase the adsorption phenomena.
Okay.
So in your system, the interaction is not good. So you have to enhance the activity. So you have to look for the other possibility, and you have to enhance the property of the system. So then you can go with analysis. That will be the general procedure to enhance the absorption of any gases towards the system.
Okay.
And you can what keep this what I mean the adsorption site, all the possible adsorption site also you have to check.
Okay.
I don't know whether you have checked with all possible absorption sites.
No. Just the top of the doped metal that
Okay,
I
so
selected.
in
On top
some
of just on top of the doped metal.
absorption site, more interaction will be what possible. That only I'm telling. Right, all the we can come to the conclusion. With respect to a single orientation and with respect to the single site study, we cannot predict anything, sir.
Okay. Noted. Thank you.
Hello, am I audible?
Yeah, yes, you are audible,
Hello,
ma'am.
thank you for your talk, ma'am and sir. I'm a research scholar and I've been using quantum ATK for a few months now. I want to conduct thermoelectric property calculation, but when I put in trigonal materials, I'm not able to convert the bulk into device. Like, is there any other way to convert the bulk to device for trigonal materials?
Actually, madam, see, you are optimizing the bulk material. That is one thing. Before optimizing, you will be having one structure. You put it into a device, then you form a device, then optimize that particular device, and you see it.
Oh, okay. Thank you, sir.
If anyone has any query, they can ask with this, sir. And if there is no query, I think we can conclude this session. Yes, after converting a bulk configuration into a device, you need to do the optimization for the better accuracy.
Madam, either you have to start with the base material, the substrate, or you have to start with the material you want to sense. You have to fix either one. Obviously, for novelty reasons, the idea is to always go for the material, the sensing material, the platform you have to choose wisely.
Also, sir, can I calculate conductivity for a bulk material, or does it necessarily have to be a device?
You have to have a device, madam. Actually, for IV characteristics, only in a device form you can do that.
Thank you, sir.
Yes. No need of conversion. Same parameters as the material. Those used for the material.
Quantum capacitation.
Hi participants, it would be better if you just unmute your mic and ask your questions. So in that case our speakers can answer. more efficiently. There are a few more questions in chat box. One is from Mr. Ani from Peru, one is from Ms. Devika Chakrabarti.
Hello, sir. Am I audible?
Yes, you can ask.
Yes, please go ahead.
Sir, like I need to calculate quantum capacitance for my material. So, is there any option to do that in like through QuantumATK? Any like
Quantum capacitor.
quantum capacitance, like for a supercapacitor? Like, is there any like workflow to do that? Like,
Yes, quantum capacitance is also possible by the QuantumATK software. So we had the tutorial as well. So let me share my.
okay, okay.
So you can see this is the QuantumATK documentation site. So here you can search the capacitance. So this is the tutorial that will help you to guide how we can calculate the atomic scale capacitance for the quantum materials. So I am sending the link as well. So for calculating the charge transfer analysis and also the water charge analysis for any material, so first you have to create a structure by using the builder tools. And once your structure is ready, you can take the structure into the builder workflow builder. And in the workflow builder, you have to set up the calculator, and then you need to select the analysis like the water charge and also the charge transfer. And then you can go for the simulation. So once the simulation complete, then you will easily get the result. So this is the standard procedure for simulating any kind of material and devices. So I think there is no query pending from anyone. So as we come to the close of this insightful session, so as we come to the close of this insightful session, I would like to extend my gratitude to both of esteemed speakers for their valuable contribution. So first and foremost, I would like to express our deepest gratitude to our esteemed speaker, Professor Kala, and also Dr. Hariharan for their enlightening presentation. So your talk on the DFT and NEGF-based atomistic simulation for the gas and VOC sensing application by using the Synopsys QuantumATK were truly insightful. You not only share the cutting edge research but also presented how the computational method can save the future of sensor technologies. Together, your combined expertise has made this seventh session of this faculty interaction webinar series both enriching and inspiring. So we sincerely thank all the faculty members, researchers and participants who joined us today and made this session interactive and meaningful with your presence. So thank you once again, and we look forward to continued collaboration and learning in these sessions to come.
Okay. So thank you, sir, for providing this opportunity. So for the audience, if you want to clarify any queries or anything, you can approach me through mail also. So we are ready to answer your questions and all the clarifications in near future. Thank you, sir.
Yeah, thank you, sir. Thank you.
Yeah, I thank the organizers and the audience who are all present during this talk. I thank each and one of you for having attended this talk. Thank you.